How do Zoom or Google Meet handle thousands of live video stream without your computer melting down? That tech that scales these calls is called WebRTC, and that's the real architecture behind live video. WebRTC is a peer-to-peer client-server protocol that enables efficient streaming of video, audio, and data. But peer-to-peer WebRTC calls are fine between two people, but what if there are three, four, or even 50 or 100 or 1,000 users on the call? WebRTC doesn't really scale to naturally to that level. You additionally need a cloud server, uh, and there are several trade-offs there. You need this cloud server to scale the WebRTC to thousands of users. So in this video, we'll overview the WebRTC protocol. We'll look at the issues in scaling it up and see how the cloud servers, and in particular LiveKit or Pipette Cloud, how do they handle this issue. So here's the basic high-level diagram on how the WebRTC protocol works. There's a client, maybe a mobile phone, which interacts with the WebRTC server, and it wants to transmit audio and video data. So first, there's a signaling layer where the client contacts the server, gets back a bunch of tracks or channels, and then it uses the video track or the audio track or the data channel to transmit the data. That's basically how this protocol works, and there are many details about how to make this work across firewalls, across different geo regions, the stun servers and ice servers and so on. But we'll not go too much into detail of those aspects of WebRTC in this video. We'll instead look at how to scale this up to hundreds of thousands of users. So for example, there are thousands of people on a particular video conference call, and you want to transmit each video's user to broadcast each user's video to all the other users. So if you look at the sender receiver pairs, there's just too many of them. You can pick 1,000 choice two pairs. So it's impossible for peer-to-peer transmission streaming to take care of that. What happens is people use a intermediate cloud server where these multiple participants talk to a powerful WebRTC server and send their streams to the server, which in turn sends it to the other clients. So it's we can view it as sender receiver pairs or publisher subscribe pairs. There are thousands of publishers and there are thousands of subscribers to this server, and the server's task is to efficiently send the incoming streams from the publishers to the subscribers. And on top of that, there could be the clients are distributed across geographies. So direct to direct peer-to-peer transmission doesn't make sense, or it will be the latency will be high. So what happens is the client connects to a server in the cloud, which connects to another server which is co-located in the same geography as the second client. This transmission between the servers inside the cloud it's highly optimized, very fast, and this servers then connects to the second client. So this indirect path ensures that the overall latency is pretty low. Okay, so yeah, as we discussed, doesn't scale because why doesn't scale? Because if say every client starts sending its 720p video stream to every other client, the upload bandwidth will be choked, as well as the download bandwidth on the receiver side will be choked. Yeah, and that's not feasible practical case. The first solution, the traditional solution is what is called MCU, multi-point conferencing unit. Okay, so there are a bunch of publishers, incoming streams that goes to this MCU server on the cloud, and all the subscribers connected to it. What it does is to merge these streams, incoming streams, into a single stream. For example, if you have video streams, the MCU server will grid them and paginate them so that one screen you have only say 40 uh, video boxes aligned in a grid, and then sends a stream to every subscriber. And there's very limited control because uh, now all of the subscribers are forced to see the same stream. They cannot vary, for example, resolution of any particular stream. They are all, it's all unified together for all the subscribers. And so while this thing works and scales, there's a lack of control per stream for every subscriber. So, so is there a trade-off? Is there something that can give each subscriber control over what they want to see, as well as keep it scalable? The idea of selective forwarding unit is introduced by LiveKit. Um, Essentially, the idea is all the publishers still talk to a cloud server, which is the SFU, and instead of merging, all the tracks are sent to each of the subscribers. So each subscriber receives as many tracks and tracks if they're in publishers. Okay, so this saves the upload bandwidth per publisher. Publishers doesn't need to talk to each of the subscribers. It saves the upload bandwidth there. But there's a trade-off here that the download bandwidth is proportional to the number of publishers. Okay, so if there are n publishers, the subscriber can download is able to download all the tracks, depends on the bandwidth, and then control them or change resolution of these tracks or do other operations on them. So, and if the bandwidth low, then the receiver client layer subscriber side can further optimize these incoming tracks and uh, and adapt to the bandwidth. So SFU is the technique used by LiveKit to support thousands of users in rooms, and a similar mechanism is used by Babcat also, the cloud server, daily cloud service. They use this mesh architecture to connect publishers and subscribers. So this is a quick diagram of how it looks on the uh, initial client server interaction. So client doesn't talk to a single server. There's a load balancer in between. Client does the signaling with the load balancer, and that connects it to a particular live server. It gets those channels for video, audio, and data, and then uses the channel information to connect by UDP to send audio, video, data on WebRTC. Servers in turn use a data store, Redis-like PubSub data stores to maintain the client and the publisher and the subscriber information. So that's a quick overview of how WebRTC can be scaled. Obviously, there are many details here which I'm not talking through, but the MCU, the cloud server, MCU, and the SFU are the core ideas on how to scale WebRTC.